Okay, in this last lecture, I am going to introduce you a couple of three species population model. In the third lecture, I discussed about single species. Then in fourth and fifth lecture, I have covered some two species interacting population model. Now we come to the three species model. First of all, I should mention here that in this lecture I will be giving only introduction to different models and then very preliminary discussion about how difficult it is to analyze the model mathematically. So, within limited time period we cannot analyze a single model completely, but I can give you the idea. So, if you are interested you can extend your calculation for this kind of problem and so on. You can recall that in case of two competitive species model, we have discussed about Lotka-Volterra two species competition model. Now we are assuming that N1 T, N2 T and N3 T, they are three competitive species. They have some intrinsic growth rate, that means they can survive independently, and of course they compete for some resources or habitat or some other favorable ecological conditions or something like that. So, for this type of model we can write down the equation in a systematic manner such that this three variable system can be easily extended to n variable system. So, first of all we can follow the same terminology that we have used in case of two species competition model, and from there we can go to the general formulation. So, idea is that independently their growth rates are defined by this R1 N1 into 1 minus N1 by K1, these things, then dN2 dt, this is equal to R2 N2 times 1 minus N2 by K2, and dN3 dt, this is equal to R3 N3 times 1 minus N3 by K3. Now the idea is that each of the species, they compete with other species in a pairwise manner for some resources or favorable habitats, something like that. So, here we can introduce that there is a competition between N1 and N2. So, here we use some alpha 1 N1 N2 in this equation, similarly some alpha 2 N1 N2 here. So, these two terms corresponds to competition among N1 and N2. Similarly, N1 compete with N3 also. So, therefore, there will be another negative term here, that is beta 1 N1 N3 minus beta 2 N1 N3. So, these terms contributes from the competition between first and third species, and finally you will be having here gamma 1 N2 N3 minus gamma 2 N2 N3. So, this is the three species competition model. Now, if you proceed in this way 4, 5, 6 and onwards, so in case of n species model at a certain time point we will not be having enough number of these Greek symbols, right. In order to overcome this we can make a generalization, and after all you can write down the entire system in a compact form. So, for this type of model you just try to understand in each of the equation there is a linear term, that is N1 multiplied with some constant, and rest of the terms they are actually pairwise multiplied. So, that means N1 multiplied with N1, N1 multiplied with N2 and N1 multiplied with N3. So, this equation can be converted as dn1 dt, this is equal to r1 n1. Without a loss of density, we are writing r1 n1 here. Then this term can be modified as a11 n1 square. So this 1 actually represents the strength of competition between individuals of species 1 with the individuals of the same species. Similarly, when we are interested to introduce the competition between first and second species and its effect on the growth of the first species, then you can write down the second term as a12 n1 n2, right? And finally, the effect of competition between first and third species on the growth of first species can be written as a13 n1 n3, right? So similarly, you can write down the rest of the equation as dn2 dt, this is equal to r2 n2 minus a21 n1 n2 minus a22 n2 square minus a23 n2 n3, and finally dn3 dt, this is equal to r3 n3 minus a31 n1 n3 minus a32 n2 n3, and finally minus a33 n3 square, right? So any one of the equation can be written in terms of general notation as d n I dt, that is equal to r I n I minus sigma j runnings from 1 to 3 a I j n j, this entire quantity multiplied with n I. So if you substitute I equal to 1 here, so dn1 dt equal to r1 n1 minus a11 n1 square, then minus a12 n1 n2 and a13 n1 n3. So therefore this entire system of 3 equations can be written as a compact form like this, where I equal to 1, 2, 3, right? Now at the very beginning I have mentioned that it would be quite difficult to analyze the stability of this system, and before stability you need to understand that finding out the equilibrium point is another difficult task for this type of problem. But mathematically we can say that apart from the trivial equilibrium or some equilibrium having some zero component, in terms of matrix equations we can provide the necessary sufficient conditions for existence of unique equilibrium point. But for the time being, if we consider the equations which are required to be solved in order to find out the coexisting equilibrium point, so therefore what we need, that none of the ni will be equal to 0, right? So therefore we need to solve these 3 system of equations simultaneously, aij, nj, j runnings from 1 to 3, this is equal to ri for I equal to 1, 2, 3, right? And depending upon the magnitudes of this aij and ri, you can understand that this is nothing but a system of 3 linear equations. So from matrix theory and solutions for system of linear equations, we are familiar with the fact there may exist unique solution, there may not be unique solution. So if there is non-unique solutions, so that means more than one solution, that can be considered as that existence of infinite number of solutions. And the main idea is that these 3 equations represents 3 planes in 3-dimensional coordinate space. So therefore, if all the 3 planes intersect them at a particular point, this geometry corresponds to existence of unique solution. Otherwise, what may happen, that there exists infinite number of solutions such that there is infinite number of coexisting equilibrium point. How it can happen? You just think about the situation that you have xz plane, you have yz plane, and another plane passing through the z axis but does not coincide with either of xz plane or yz plane. So therefore, you have one plane like this, another plane like this, another plane like this. So all these 3 planes, they intersect along a straight line. So you will be having infinite number of equilibrium points, and judgment of stability in that particular situation is quite difficult. And also there may be a situation that these equations are not consistent, or they are inconsistent, such that you can have some pairwise solutions, but there does not exist any solution which will be satisfying all the 3 equations. And simple geometry involved with this is that you can think of 3 planes, they are situated in this way. So this is the dotted one, this is this one, and this is this one. So this plane represented by one equation, this plane represented by another equation, and this plane represented by the third equation. So pairwise there exist infinite number of solutions, but there does not exist any unique solutions. So first part is quite complicated. That means itself finding out the equilibrium point, and then finding out stability is much more difficult situation. But in principle, you can assume that this coefficient matrix is invertible. So if you assume this coefficient matrix is invertible, then there exists unique solution, and under such condition you can find more than one equilibrium points apart from the coexisting equilibrium point. Because if you look at this equation, there is a trivial equilibrium point of the form 0 0 0, right? Then there exist 3 equilibrium points on 3 coordinate axes. Those corresponds to first species exist at their carrying capacity, second and third species are absent. So that means equilibrium points of the form R1 by A11, second and third components are equal to 0, right? Similarly, 0 R2 by A22 0, and there will be one more equilibrium point 0 0 R3 by A33. So therefore, these are some equilibrium point where at a time 2 competitive species is going to extinction. Similarly, you will be having another set of 3 equilibrium points for which 2 species coexist, but third species will be going to extinction. So that means there will be equilibrium point of the form, say, alpha beta 0, alpha 0 gamma, and 0 beta gamma, and finally you will be having coexisting equilibrium point. And depending upon the magnitudes of R1, R2, R3 and other coefficients, you can find out stability of those equilibrium points, and also depending upon the strength of the competitions, it may happen that suppose an equilibrium of the form alpha beta 0 is stable, right? So that means the third species is much more weak competitor compared to the first and second species, such that they will not be able to survive, rather they will be going to extinction, and you will be having coexistence of first and second species. Similarly, these kind of situations can appear in case of second and third or first of third, this type of combinations. So, this is the general format for 3 species competition model. Now, next interesting model is the food chain model. Food chain model is something like that. You have 3 species under consideration such that we are not interested to model the resource of first species explicitly, but we are interested to model the pattern of consumption and growth of second and third species depending upon the abundance of first and second species respectively. So, the idea is that there is a n basic food source, then you have p, so that means p survives on n, and then there is another species say z, where z survives on p. So, the idea is that in the food chain, this is the basic level, this is the first level. So, p is a predator for n and z is a predator for p, right. So, in this kind of situation, the model will looks like, suppose this n grows with logistic growth law. So, therefore, Rn times 1 minus n by k, and without a loss of generality we can assume that grazing pattern of n by p and grazing pattern of p by z, they follows the same functional response, but with different parameterization. So, therefore, we can assume that grazing of n by p is described by say alpha 1 np divided by beta 1 n, then this particular consumption of prey by the predator will contribute to the growth of first predator. So, that there will be one conversion efficiency E1 alpha 1 np divided by beta 1 plus n. So, this is the growth of first predator depending upon the presence of prey population n. They have some natural mortality rate, that is minus m1p, and this p is again consumed by z. And as I have mentioned that we are going to model these things with same type of functional format, functional response. So, therefore, you can write this will be minus alpha 2 pz divided by beta 2 plus p, correct, and finally dz dt, this is equal to E2 alpha 2 pz divided by beta 2 plus p minus m2 z. This is a food chain model. In some of the references you can find this is a prey predator top predator model, and mostly this model is known as Hastings-Powell model, and they have considered this model as a food chain consist with phytoplankton, zooplankton and the fish population. So, in order to analyze this particular system, you can consider the corresponding non-dimensionalized version, and again you can write it into the compact form like dx dt, this is equal to x into 1 minus x minus f1 x into y, then dy dt, this is equal to f1 xy minus f2 yz minus some p1 y, and dz dt, this is equal to f2 yz minus p2z, where this FIU, this is defined by AIU divided by 1 plus BIU, where I equal to 1, 2, right. Now with this notation, with this particular notation, I just like to remind you that if you remove the third species from the system, that is if you remove Z from the system, then this will go back to classical Rosenwig-McArthur model. And if you recall the parameterization that I have considered in my previous lecture, so here parameterization is little bit different. Now I want to draw your attention with this kind of format of the functional response or some sort of non-dimensional scheme through which you can find out this as the dimensionless functional response. It is somehow beneficiary to compare the dynamics of the system with two different types of functional response. What are two different types of functional response? You can observe that if you choose B1 equal to 0, it will go back to holding type 1 functional response, and if B1 not equal to 0, this is holding type 2 functional response, right. So therefore, once you will be having the result for the entire model with B1, B2 are both not equal to 0, then as a special cases you can consider or you can derive some conclusion towards the situation that okay, interaction between first two species follows the holding type 1 functional response, whereas the interaction between second and third species follows holding type 2 functional response. So in some sense this particular parameterization have some utility towards the getting conclusion about the system where instead of holding type 2 functional response we can derive the conditions which some of them are holding type 1 also. And again for this type of system, if you find out the equilibrium points and then perform the linear stability analysis and then bifurcation and so on, so there will be couple of different types of equilibrium points. So one will be of course trivial equilibrium point, then you will be having equilibrium point of the form prey only equilibrium, then there will be another equilibrium point where prey and predator are present but top predator is absent, and finally you will be having coexisting equilibrium point. But in order to judge the stability of this system, now your Jacobian matrix evaluated at any one of the equilibrium point is a 3×3 matrix. Now for 3×3 matrix, if you just want to check the stability or implicitly if you want to derive the condition of stability, the best possible way is to use Routh-Hurwitz criteria for the stability. So Routh-Hurwitz criteria says that when you will be evaluating the Jacobian matrix at any one of the equilibrium point for this 3 species model, then your characteristic equation will be of the form lambda cube plus a1 lambda square plus a2 lambda plus a3, this is equal to 0. And for local stability what we need, that this cubic polynomial equation will be having 3 roots. So we need real parts of all the eigenvalues should be negative. This is a most general statement. So possible combinations are all the 3 eigenvalues are negative real numbers, or 2 of them are complex conjugate eigenvalues with negative real part, and third one is the negative real number. And as per Routh-Hurwitz criteria, we can ensure that real part of lambda j, this is less than 0 for j equal to 1 to 3 whenever a1 greater than 0, a3 greater than 0 and a1 a2 this is greater than a3. So whenever you will be evaluating the Jacobian matrix, from there you can write down the characteristic equation. So then all these coefficients will be some complicated function in terms of the parameter involved with the model system, but at least you can derive the parametric restrictions by demanding that a1 greater than 0, a3 greater than 0 and a1 a2 greater than a3. So you can understand that when you will be finding out the equilibrium points for this system and deriving the Jacobian matrix, it will be quite complicated structure, and from where ultimately you will be able to derive some parametric restriction, and afterwards you need to take help of either some numerical method, that means you need to substitute some of the parameter values to check whether the stability condition are satisfied or not, or you can do one thing, that you can try to find out the common parametric domain either in two parameter space by substituting numerical values for rest of the parameters, that where all these three conditions are satisfied. And if any one of these conditions is getting violated, then interior equilibrium point is not stable, and of course there is a well established theory to prove that how destabilization can take place. Now theoretically this destabilization can be of different type. So one possibility is that interior equilibrium point is becoming unstable due to Hopf bifurcation, that is one possibility. Other possibility is that interior equilibrium point may coincide with any one of the boundary equilibrium or axial equilibrium. Because in case of Rosenwig-McArthur model, you can recall that I have mentioned that interior equilibrium point can coincide with the axial equilibrium point 1, 0, right. So here in this model, if we just draw a rough sketch of the possible positions of the equilibrium points, so this is your x axis, this is your y axis and this is your z axis. So here you will be having one equilibrium that is 0, 0, 0, trivial equilibrium. Then you will be having one equilibrium point here, that is say alpha 0, 0 without any loss of unity. That means first component is non-zero, second and third component they are exactly equal to 0. Trivial equilibrium, axial equilibrium. Then you will be having one equilibrium point here, say alpha 1, alpha 2, 0, right. And finally you will be having some interior equilibrium point here, that will be having some component x star, y star, z star. Now the idea is that these equilibrium points are actually points of intersection of three-dimensional surfaces obtained from these equations by deriving the corresponding non-trivial null lines and their point of intersection with the coordinate axis or coordinate planes, right. So under certain parametric restriction, what you can do, you can move this equilibrium point towards this point and it may coincide with this one. So this can happen under certain situation where z component, that means the top predator, is going to extinction. Now here, as we have assumed that y survives only on x, z survives only on y, so there will be no equilibrium of the form that first and third components are non-zero but middle component is equal to 0. Because if you substitute y equal to 0 here, so as per this functional format, this term is exactly equal to 0. So growth equation for z is dz dt equal to minus p2z, p2 is a constant, so it clearly shows z will be converging to 0 implying Z species become extinct. But the point is that depending upon the type of interaction, there are several other types of population models also in 3 dimension, and you can have different possible combinations. Just 2 examples I can provide here. Suppose you have a predator species. This is a generalist predator in the sense that it has 2 separate food choice. Just for example, you can consider the interaction between deer, ox and tiger. So type of food source availed by deer and ox, they are same because they are vegetarian. So their food source is some autotroph species, and we can assume they are abundant in nature. So for the time being, desperately we can assume that we do not need to model the growth rate of the autotroph. Rather, we are interested to study the situation that when predator survives on true prey species, then there will be 2-3 different situations may come out at the end of the analysis. So depending upon their grazing pattern, depending upon the growth rate of both the prey population, there might be some sort of competition between 2 prey species for the same resources, or maybe with the assumption that carrying capacity for both the prey having the same parameterization. So there are 3-4 different types of modeling approaches. So for the time being, I can explain some of them precisely. Suppose that N1 and N2, this denotes the 2 prey population and P is the predator, right? And we are assuming that growth of N1 and N2, they are independent to each other. So they have individual growth rates and their carrying capacity is not affected by the abundance of other species. So therefore, we can have this type of equation dN1 dt is equal to R1 N1 into 1 minus N1 by K1. This is the growth for first species in absence of predator, and dN2 dt, this is equal to R2 N2 times 1 minus N2 by K2. Now, based upon which aspect we can have 3-4 different models. So first aspect is that we can take care of the fact that N1 competes with N2, N1 competes with N2 for some limited resources. So based upon that, you can introduce minus alpha 1 N1 N2 term here and minus alpha 2 N1 N2 term here. But for the time being, we are assuming there is no interaction. So that means resource required for the growth of N1 and N2 are abundant. Next, we are assuming that N1 is consumed by P, predator, N2 is also consumed by P. So therefore, we will be having this kind of term, say minus F1 N1 P minus F2 N2 P, right? And then growth of P is defined by E1 F1 N1 P plus E2 F2 N2 P. So these are actually growth due to consumption of first and second prey, and finally their intrinsic mortality rate minus MP. Again, you can think about these functional forms. Functional form means depending upon the body size of the individuals and particular species under consideration, these two functions may be of similar type, may be of different type. Just for an example, you can consider F1 is holding type 1 functional response and F2 is holding type 2 functional response. If you interested to have detailed discussion in this direction, you can just look at the book by Peter Turchin, that is Complex Population Dynamics. In that book you can have examples of different species and how the functional response are actually chosen depending upon some available data for ecological interaction. You will be having some nice discussion on that. But apart from that, you can think about one more modification. So from mathematical point of view, we can propose several types of models. Sometimes it seems to us that okay, this is just a mathematical model, nothing to do with the biology. But in reality, you can think about that okay, P survives on both N1 and N2, then why we are not thinking about the situation that grazing pattern of N1 by P is influenced by the presence of N2? Why not? So in that case, what will be the modification in the model? Modification will be F1 N1 N2 P, F2 N1 N2 P, and accordingly these arguments will be N1 N2 and N1 N2. And most of the time this type of functional form, a particular example is suppose your F1 N1 N2, this is equal to A1 N1 divided by 1 plus B1 N1 plus B2 N2. This is one possible format. So if you proceed with this kind of formulation and analyze the entire model, of course you need to keep in mind that analysis of this model is quite complicated. You might not be having components of interior equilibrium point explicitly. You need to take help of some rigorous mathematical technique or some numerical approach in order to study the behavior, because once you are considering this type of functional form, then it will be quite difficult to find out unique solution by solving three equations of the form, that is N1 will be taken out from this one, rest of the expression is equal to 0 and so on, and their stability cannot be obtained explicitly in terms of the parameters. But once you will be having some numerical values of these parameters, you can use some numerical scheme or some software like Mathematica or Maple, where you can find out the components of the equilibrium point numerically and judge their stability behavior. But the idea is that once you will be considering this type of formulation, it will give you much more generalized result, because the earlier result can be obtained by substituting B2 equal to 0 and in the second case this B1 equal to 0. Now there is a group of researchers who are interested to give emphasis on this type of functional form with the claim that okay, still we can modify this model. Why? Because if I want to consider prey for P as a single resource, then the prey population N will be equal to sum of N1 plus N2. So mathematically we need to write down this model in such a format that when you will be considering B1 equal to B2, A1 equal to A2, R1 equal to R2 and K1 equal to K2, then entire model will be converted to a single model of the form, that is dn dt equal to one equation and dp dt this is equal to another equation, and where n equal to n1 plus n2. Right. Now from this stage, if you want to derive this kind of model, it is impossible. You can do it if you introduce one more modification into this particular modeling approach. What is the modification? If you consider R1 equal to R2 and K1 equal to K2, so you can have the sum of R into N1 plus N2. but here you will be having r by k n1 square plus n2 square, right. So you cannot take n1 plus n2 whole square. So what additional term you need to introduce here? That is interspecific competition term among the n1 and n2. So there are two different approach, either based upon this kind of demand that if I want to consider n as the sum of both the prey population and we are interested to derive this kind of model, then it is possible whenever you are having this interspecific competition term or this type of logistic growth, this growth term can be modified by writing n1 plus n2 here and n1 plus n2 here. So therefore nothing but you are actually introducing one competition term, that is n1 multiplied with n2 and here n2 multiplied with n1. And likewise you can extend these things into 3, 4 and 5 different possible resources, and in that sense here predator can survive in absence of either of the prey population. So in some sense this type of 2 prey 1 predator model is also known as 2 prey and a generalist predator model, because this predator is not surviving only one food source, rather it has 2 different food sources, one is n1 and another one is n2, right. Lastly, I just mention one more 3-dimensional model, that is known as prey predator model with Intraguild predator, and the idea is that you have one prey, 2 predator, but second predator can survive on prey as well as on the first predator. So therefore general formulation will be something like this, that is dn dt, that is equal to n into fn, that is growth of n in the absence of 2 predators. First predator consume prey population, say p of n multiplied with p1, this term contributes to the growth of first predator, that is dp1 dt, that is equal to e times pn times p1 minus some m1 p1, and then second predator p2, this survives on both prey and first predator. Hence there will be one term here, that is p1 n p2, contribution will be e1 p1 n p2 minus p2 p1 p2, so plus e2 p2 p1 p2 minus m2 p2, right. So this is prey, predator, again this is somehow generalist predator, but specifically it is called Intraguild predator, and this type of model have some special cases, like within oceanic environment you can consider the interaction between 2 fish population. Sometimes it happen that larger individuals of a certain species, they can consume newborn of the same species. So therefore in other words we can consider that this is a some sort of stage structure for a single species where P1 is the juvenile and P2 is the adult, such that this fish population survives only on this particular resource, but adult individuals of this species can consume the juveniles of this particular species. And there are some other examples also in ecology, that some of the species they can survive on two different type of resources, such that their first resource is consumed by the second resource also. And of course, in this case you can think about, there will be one equilibrium, that is trivial equilibrium, forget about it. Next one, only n is there is no predator, and apart from that you will be having equilibrium of the form, say n bar p1 bar comma 0, then n double bar 0 p2 double bar. Because from this particular system you can take out two species model, two species interacting model, assuming that either P1 or P2 is absent. And when you will be considering those type of model, that means if you consider P2 is absent, then this equation will not be coming into the picture, these two terms will be absent. So you have a Gauss type prey-predator model. Again, if you ignore P1 here, so then this term will be absent, this equation will not be coming into the picture, this term can be set to 0, again you have another Gauss type prey-predator model. And depending upon this kind of structure, you can think about in P1, P2 and n plane. So suppose this is your n axis, this is your P1 axis, and this is your P2 axis. So what are the equilibrium points? This is a trivial equilibrium point. Here you will be having one equilibrium point on n axis, then you will be having one equilibrium point on np1 plane. So that means it has the components n bar p1 bar comma 0, another equilibrium on this particular plane, that is n double bar 0 p2 double bar, and finally one interior equilibrium point, that is n star p1 star p2 star. And of course you can have different functional forms for this P, P1 and P2, and accordingly finding out this interior equilibrium point explicitly will be quite complicated task. But somehow if you have the numerical values of the parameters, then at least numerically you can find out the equilibrium points, or alternatively you can substitute all the parameter values except one and perform the one parameter bifurcation analysis and different type of approach to understand that how grazing pressure on prey population by the first predator or grazing pressure on prey population by the second predator, they can influence the dynamics of the system. And if we consider this type of model in 4 and higher dimension, you will be having too much complicated expressions, and most of the time you might not be able to find out any analytical result for the system under consideration, and you need to take help of completely numerical approach in order to draw some conclusion. But of course, in other words, this type of problem is very interesting to some of the people who are interested in nonlinear dynamics from nonlinear dynamics point of view, because it has capability to show a wide variety of rich bifurcation structures. And here up to this point I have discussed all the cases with logistic growth. You can think about two prey one predator model where both the prey population or either of them is affected by allele effect. So, model will be becoming quite complicated, but there are some interacting species which can be accommodated with such kind of modeling approach, but not for the entire parameter range, but for a very narrow parameter range depending upon the type of interaction or type of species you are having and also with the available data set. And of course, these type of models again can be modified further, that here we are assuming that grazing pattern of n by P1 is not influenced by P1 itself. So, for example, here you can assume that as P2 survives on P1 population, so that means first predator, so this grazing pattern can be a function of not only n, rather it is a function of n and P1 also. But of course, there is some sort of debate that which one is the most suitable modeling approach. And the problem is that if you have some realistic data set, you need to understand what is the ecological mechanism going on between their interaction. There is no mathematical tools available so far such that your time series or observed data will guide you to choose appropriate functional format. Only you can observe the grazing pattern, their behavior, etc., and then with the available literature or available functional form, you can try to estimate the parameters and try to match the model prediction with the available data set. But there is no mechanism by which you can decide that okay, for this type of interaction I need to consider Holing type 2, or for this type of interaction we need to consider Holing type 3, and so on. So therefore, choice of functional response is completely in our hand. Rather, we can say we need to choose this functional response in a judicious manner such that it will be able to capture the behavior which are exhibited by the interacting species. And of course, this type of model in 5 and higher dimension can be extended with the assumption that okay, you have 3 prey, 2 predator, and all possible type of combination what I have considered here. So that means 2 predator, they may compete among themselves for the available resources. There are some possibility. Or you can think about that 3 prey species, they are competitors, and those prey individuals is predated by 2 different predators. And it is possible to show that okay, in the absence of 2 predators, they cannot survive because their competition rate is quite high. But with the same situation, if you introduce some predator, so what is happening that if the grazing rate of strongest competitor by the predator is quite high, so then they can lead to some sort of coexistence scenario. And the idea is that in open environment ecological system, we cannot truncate any species at any level because there are different types of hierarchy and they have different types of food source. But mathematically we can try to construct some model and analyze them to give some sort of prediction just in order to match with the data. And of course, the parameter estimation is another interesting task or important task here in order to have some accurate prediction for the system under consideration. Right. So I can stop at here. Any 1 or 2 quick questions?
Yeah, in this route approach criteria, you choose A1 greater than 0, A3 also greater than, and A1, A2 greater than.
This is the condition.
I didn't understand why you chose that.
No, this is not my choice. if you consider that there are 3 roots of the form alpha plus minus I beta and gamma such that alpha less than 0 and gamma less than 0, then using complex variable theory you can derive these are the conditions required to be satisfied such that all 3 eigenvalues will be having negative real part.
For this real part of lambda j,
Yes.
that will come.
Yes, yes. And this type of result can be extended to n dimension also. And a quick reference is the appendix of J.D. Murray's book. They have given a complete compact matrix structure for general n to find out the sufficient condition for the local stability. So that means all the eigenvalues will be having negative real part, right? Okay.
Because we talk about ecology, I mean all these predator-prey interactions and all, we only deal with equilibrium, right? There's no point of
No.
thinking about chaos.
Yes, because Hastings-Powell's model, that is food chain model, it exhibit very rich global dynamics. It shows some sort of chaotic dynamics. And finding out the ecological cause behind the generation of chaotic dynamics, and also mathematically you can try to detect what is the root to chaos. And there are several literatures where you can find either period doubling route to chaos or crisis route to chaos or intermittency route to chaos. And then you can think about, okay, this model predicts some sort of chaotic dynamics, but the system under consideration I cannot observe any chaotic oscillation. That is possible because for which parameter value you are observing here some chaotic dynamics, that is not realistic for the system under consideration. So once you are performing the complete bifurcation analysis, so you are free to choose any one of the parameter values. But just for example, if you consider the phytoplankton growth and time unit is taken as per day, so the growth rate will be at most 2, because one phytoplankton cell can be divided at most twice within 24 hours time period. But this growth rate is equal to 2 is not true for the human population if you consider the time scale as or time unit as per year, and they vary from one species to other species. So mathematically we can derive, okay, this is the condition, under this condition we will be having some chaos, but we need to check whether this type of parameterization or choice of the parameter values is either consistent with the system under consideration or not. For example, mathematically you can say that if carrying capacity is equal to twice the growth rate, but in general growth rate is much less compared to the carrying capacity, right? With different type of parameterization you may not have that A1 in both the equations, that is for x and y that I have written earlier, that is FIU equal to this one. Now you are having some sort of result where the contribution to the growth of predator from prey is higher than the rate of grazing. So mathematically this result can come out, but that is not realistic, because if you think about the amount of food we are taking every day and its contribution to the growth, so after certain age there is no observable growth at all. So entire food is getting converted to the energy. So the idea is that what time scale, what is the population level, everything you are considering, that makes an important contribution towards the choice of the parameter values, right?
I have a question, like, so this approach can it be applied to this cancer cell proliferation?
Yes, exactly. There are several works by different group of people, I forgot the name, Takwell have done some sort of stochastic modeling on this, and there are several groups that are working this type of equations with cancer growth and etc.